My name is Danielle Venton. I'm a science reporter at the local NPR member station, KQED. I hope some of you listen. And it is my great pleasure to be joined by our panelists this evening, both very distinguished physicists. Right here to my side is Fabiola Gianotti. She is an acclaimed physicist and Director General of CERN, the European Organization for Nuclear Research, and she's made groundbreaking contributions to the field of particle physics, notably for her leadership role in the discovery of the Higgs boson at the Large Hadron Collider, which we just learned all about. Her research focuses on understanding fundamental particles and forces that make up the universe, and her work has earned numerous accolades and really cemented her reputation as a leader in the international scientific community. In 2012, she was named runner-up for Time Magazine's Person of the Year, which not many of us can say. And beyond her scientific achievements, she's an advocate for international collaboration in science education and has been a prominent voice in promoting scientific research and its impact on society. We're also joined by Hitoshi Murayama. He's an internationally renowned theoretical physicist who has spent his career exploring fundamental forces of the universe. He is currently the MacAdams Professor of Physics at the University of Berkeley, faculty senior staff at Lawrence Berkeley National Laboratory, professor at the Kavli Institute for Physics and Mathematics of the Universe at the University of Tokyo, and he is a passionate advocate for science education and outreach, and he is currently the chair of the U.S. Particle Physics Project Prioritization Panel, P5, because that's quite a mouthful. And this group recently defined the strategic plan for national particle physics in the US. So we are so lucky to have both of you tonight.
Thank you.
Now, you both have distinguished careers. You've known each other for a long time, but I would like to start our discussion talking about what got you into particle physics and what kept you there. Fabiola, would you like to start?
I wanted to be an explorer. But I failed. And so, no, seriously, what brought me into particle physics? I was a very curious child. And when I was a child, of course, I was asking myself many questions. I was asking adults many questions. Very rarely I got satisfactory answers. The web did not exist because it was invented at CERN in 1999, so I'm doing some advertising for CERN. So I could not Google and, dark matter, dark energy. No, it was not possible. So that's actually what attracted me to physics. I really wanted to understand how things work at the most fundamental level. So I would look at the sky and I would try to understand the stars, why they fall on our head, or understanding how things work, how if I just cut this cake into smaller pieces, what do I get at some point, where do I get? And so I because actually at high school I've been studying humanities and music, so nothing to do with science, the few hours of math and physics at school actually attracted me to understand a bit better, and I decided to study physics, and so at university. And it was a little bit of a jump into the dark because I didn't know what I would expect, and I was so happy afterwards that was really what I wanted to do. And I became a particle physics exactly because particle physics, as Danielle explained, is the most fundamental of all sciences because it looks at the most fundamental constituents of matters and of the universe. And so in some sense, I think today that I was looking for this simplicity which explained the complexity. Nature is very complex, but actually when we look at the foundation of nature, it's so simple, so elegant in its simplicity, and I think Danielle explained this very well. So that's it.
Hitoshi, what brought you here and what kept you in this?
Yeah, well, before I start this, Daniel gave one fantastic talk, but there's one thing I disagree with you. I'm not Rolling Stones, I'm not that old. Just to make it clear. So anyway, so I got fascinated by physics partly because I knew I was not going to be an explorer. I was a very sick child. I had a very bad case of asthma. I probably missed like a third or quarter of my school days. So I had to stay home a lot. And when I stayed home, all I could do was turn on TV. But the turning on TV, there was actually great educational programs I really enjoyed. And that actually got me think, really sort of naive questions like, why is the sky blue? Why do my legs look shorter when I get in the bathtub? And I was fortunate that my dad also had a physics background. And when I asked these naive questions, he could answer many of them.
Lucky.
So I got really attracted to this idea that, okay, questions have answers. And eventually came to the point that everything is made of atoms, and atoms are made of only 3 things, and so on. So then I got really fascinated with this idea that the answer is actually simple. And that's something I really wanted to pursue.
Simplicity.
Eventually to the point that now I don't what I'm talking about, as Daniel explained beautifully earlier today. So that's my route, how I ended up being a physicist.
Fabiola, what is it like to be head of an organization like CERN? You work with scientists from all over the world. CERN is home to some of the most interesting discoveries in physics and has produced some really incredible technology that we all use every day.
Yeah, so exactly. So of course it's a great privilege, a great honor. And what is very special being at CERN, in general, being the head of CERN, but being a CERN scientist, is that it's first of all our mission, which is to understand the universe and matter at the most fundamental level. So answering actually the question that were mentioned before, and the question I've been with humanity since for centuries and thousands of years. Where do we come from? Where do we go? Is our universe stable? Today we think it's not. So I don't want to scare you, but but it's not for tomorrow. Maybe in a few billions years from now, the universe will not exist, no longer exist. How matter was formed in the early universe. This is related to the Higgs mechanism. So these kind of objectives are so sexy, really beautiful. At the same time, in order to accomplish our mission and to answer those questions, we need to develop cutting-edge technologies in many, many fields. So from superconducting magnets to fast electronics, from technologies related to big data and computing, to cryogenics, vacuum, and so on and so forth, with very important application on society, as we saw in the video. And we do so in a truly international environment with people from all over the world. CERN has a community of 17,000 people. More than 110 nationalities are represented. So it's really working together on the global scale. All of us and some of these people actually come from countries that are not the best friends of each other, and still we work together. So it's really doing something beautiful and noble, I think, like pushing, the limit of knowledge, pushing back the limit of knowledge, and doing it with the rest of the world. So it's really fascinating.
Hitoshi, you have a lot of responsibility too. You've led organizations and institutes, and right now you're helping steer the U.S.'s involvement in future particle physics. Tell us about that role and why you wanted to do that.
I didn't want to do it.
Tell us about that.
So I actually would like to ask Gina, who is the director of Office of High Energy Physics, why they picked me to actually do this job. So I actually don't know. Actually, when I was told that I should take this role of making decisions on what we should do in the United States for the future of particle physics, I told the people at Department of Energy, I'm scared to death. And one of them, Kathy Turner, jumped on me and said, that's your qualification. What do you mean? I'm scared and qualified? And what she told me was, well, we get a lot of people who tell us that that's easy. I know the answer. I know what we should do, so let me run it. And that's the kind of people they didn't want, because I at least understood the gravity of this responsibility of making major decisions that would affect thousands of physicists in the country. So being scared was the reason I actually did it.
I'd love both of your thoughts on the current state of high energy physics. Before I was a radio reporter, long before, I worked at CERN a little bit in the mid-2000s, and I remember then physicists were so eager for seeing beyond the standard model. And it seems that we are still at that point. How do you feel about the current state of things? Is physics stuck at this moment?
Theorists first or experimentalists first?
Yes, we have a theorist.
Theorists are up there in the air.
All right, let's hear the theoretical answer.
Well, as Daniel said already, we know we don't understand so many things about the universe. We have very little clue how it works at all. And I came today wearing a T-shirt on dark matter because I don't know what it is. But I also happen to think that dark matter is my mom because she assembled stars and galaxies from primordial gas. Otherwise, I wouldn't have been born. So it's part of the question, why do I exist? Where do I come from? And I can't stop thinking about it. And there must be an answer to this question, too. It's just that we haven't gotten there yet.
Yes.
Mm-hmm. Did you think we would be there by now?
I certainly hope so. And of course, there's no guarantee. Yeah. But how much we have learned over the last several centuries is so staggering. And just thinking about the past, I'm very much optimistic that we will learn a lot in the next decades, too. So I'm very much looking forward to that.
Yeah, so Daniel and Hitoshi have both talked about the known unknown. We don't know the composition of dark matter, but we know it's there. We don't know what dark energy is, but we know that there is something that is pushing and pulling the universe apart. So the interesting thing are also the unknown. So in some sense, one of the goals of what we are doing in our exploration of fundamental physics and the universe is to really understand what are the right questions to ask, because there may be many question marks that we are not aware of yet. So it's an incredible and beautiful path which will never end, fortunately. But it's true, it's a very special time in particle physics because we have understood a lot now with the discovery of the particles that Daniel showed. The Higgs boson was the last particle that the standard model, the theory that described the elementary particles, had predicted, and it was not yet been discovered. But there are this big known unknown, and maybe many more unknown unknowns, which of course make our life extremely interesting. Our life, I mean humanity's life, very interesting. And so I hope, I don't know if we will be able to solve the problem of dark matter during our lifetime. I hope so. I'm young, you are much older, but okay.
I'm Mick Jagger, apparently, so.
But one thing I really have admiration for an experimentalist like Fabiola is that she gets to talk to the universe directly. So experimentalists build instruments that allow them to talk to the universe. And theoretical physicists like myself sit in the background and twiddling my fingers while waiting for the answers to come out. So I'm really sort of great admiration to experimentalists.
But even worse, the theorists tell us, look at that. We look at that, search in that direction, nothing. Look at that. We go in that direction, nothing. Sorry.
Sounds like my role is mislead people.
No, I'm joking.
It's a conversation, though, right? Between
it's
theorists
absolutely important. It's
and,
theory and experiments, work hand in hand, and it's absolutely important. This dialogue is very important.
Well, so that's related to my next question. Often in physics, a discovery is encapsulated in a particle. A new particle is discovered. But for the better part of the last century, there have been particle accelerators in the US, at CERN, all over the world, and not all of them have discovered a new particle.
Yeah.
How do you determine whether an accelerator is successful?
Well, one of the accelerators CERN hosted, LEP, that was shown in the video, didn't discover new particles at all. But it was an amazing success.
Absolutely.
It actually, thanks to that accelerator, we now understand how weak interaction works. Before that accelerator, we didn't. And Daniel talked about in WZ particles that mediate the weak interaction. And we haven't studied them very well before that experiment. So the discovering new particle is not the only purpose of a new accelerator. Trying to understand how things work is also a very important part of the job.
Yeah. And I know that it's not just scientists and their careers that benefit from particle accelerators. We all benefit. I wonder if each of you could talk a little bit about that, about some of the specific applications that have come from this world, this research.
There are very many. You have seen some of them in the video. As I said, fundamental research is a driver of innovation. What does it mean? Not just in particle physics, but in many other fields, but in particular in particle physics. What does it mean? It means that the technology that fundamental research needs do not exist at the time when we need them. And so we have to push for them. We have to develop them in our laboratories. We have to build prototypes. We have to make mistakes. We have to try. We have to work hard. And then in this way, in some sense, we open the path. We are pioneers in our exploration of technologies. We open then the path to industry and to application to society. So example of application also mentioned in the video are accelerators used to treat cancer. When you want to treat a cancer, you usually use X-rays. X-rays have the problem that when you irradiate the patient, they spread everywhere. On the other hand, if you use proton or light ions, like carbon ions, those beams are much more focused, so they can hit the tumor, release a lot of energy in the tumor without touching the surrounding tissues. So it's this kind of accelerators this kind of treatments are preferred in some kind of tumors. And these accelerators, these machines, are built on technologies developed at CERN or in other research centers. Medical imaging, the positron emission tomography, the PET, which is one of the most widely used scanners today, is based on technology developed at CERN. Vacuum technologies developed at CERN are used in solar panels, so for the environment. We develop superconducting cables, which allows us to transport thousands of amperes of energy and electricity without losses, and these, of course, are also very important for society towards, improve sustainabilities and so on and so forth. So there are many, 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 and that's an important spin-off of fundamental research.
And let me also add that many of you in the audience actually own particle accelerator at home, microwave oven. They use tiny particle accelerator to produce microwave, and that actually heats up your food. So you actually have one at home.
Yes. And we didn't mention the web, of course.
We've heard about it in the Bay Area.
Yes.
I want to talk about the future and where we should go experimentally, and also how you decide where we should go, as a community, where we should go experimentally.
Well, as Danielle already mentioned, I had to be make decisions in recommendations, at least the funding agencies, on what project we should embark on in the next 10 to 20 years. And that was actually a very difficult question, because the people in the community, physics community, are so creative. They came up with all kinds of different ideas what should be done. And if we add up everything people propose, that would go like 10 times more than what we can ever afford in science in the United States. So it's a tough question. But in the end, we had to boil down the question to what is the most important science, what is the thing we think we can do in the next 10 years, and then became pretty clear what we should be doing. And one of them is a new accelerator, which may happen at CERN, called FCC. And the reason we are gathering around this week in San Francisco is because we have a workshop, and a bunch of scientists, 460 of us, actually got together and talk about how we can use this new accelerator, if it can be built, to actually explore the properties of the Higgs boson you heard about. And the Higgs boson is actually, in my mind, a superhero.
Yes.
Because it's actually keeping us in one piece. Higgs boson is everywhere in the universe. It's frozen everywhere for some reason. We don't know why, but it's there. But if the Higgs boson disappears for some reason, everything in your body starts to fly with the speed of light, and you would evaporate in a nanosecond. So thanks to Higgs boson, we stay in one piece. That's why I say it's kind of
exist also because of that.
So what we like to understand is how it actually keeps up in one piece, and why is it there to begin with. And that's something we haven't understood yet. And the new machine, like FCC, can potentially answer the question, and that's why so many physicists came together to talk about this machine in the future. And that was actually one of the recommendations we made.
Yeah.
Can you tell us a little bit about the timeline of I believe right now it's in a study, sort of exploratory phase, the future circular collider?
Yeah, at the moment, of course, these are big machines, very complex, technologically very challenging, and so it requires a lot of preparatory work. We are at the moment doing the feasibility study. For the moment, we have found no showstopper, except maybe money, but okay, it's a little. And so the timeline will be to get the machine approved, if it is approved before the end of this decade, to start construction at the beginning of the next one, and then operation in the middle of the 2040s. So looks like very far into the future. But CERN at the moment is running the Large Hadron Collider, which will be operating until 2040, 2041. So clearly we have a lot of things to do. And in parallel, we will be building the next collider. There is Hitoshi explained it very well, but I think there is consensus today in the particle physics community worldwide that the next step is really to a machine, a collider, that allows us to study this very special particle, the Higgs boson, which is really the simplest object and maybe the most puzzling objects we have ever discovered. So simple, but at the same time so mysterious. And to study it in all details, to understand what happened in the very early universe when the so-called Higgs field settled, and where the universe will go in the future.
And actually, many people in the US community wanted to build such a machine on the US soil, because it's such an exciting thing to do, and such a great mystery to be solved. Mm-hmm. But quickly we realized that US budget doesn't allow for it. We couldn't afford it. Mm-hmm. But fortunately, Fabiola has been talking about it already in Europe. Potentially there's another machine people are talking about in Japan as well. So the beauty of a field is that, if you can't do it alone, you get together. And that's how we came up with the recommendation that we should join forces and to build such a machine somewhere in the world. And FCC is definitely a great candidate.
But actually the United States is doing something very interesting at the moment, building a project to study neutrinos, and Danielle explained neutrinos as this very elusive particle that also play an important role in the universe, and we want them to understand their features, and they are so difficult to capture because they are elusive, and so we need, very high intensity beams, very powerful detectors. So there is a project run by Fermilab that will allow us to understand the nature of neutrinos. So the US is also doing very interesting things. And an important thing is to actually that we try to collaborate worldwide and across the world, and having complementary facilities. So people, for instance, that today want to work at the energy frontier, work at CERN, at the Large Hadron Collider, the European that want to work on neutrinos, come to the United States. So it's a very nice way of collaborating across oceans.
If we could transport ourselves to 2040 and the FCC is already built, what would you be most excited about? Would it be exploring the Higgs field?
Yes, absolutely. Yeah. Absolutely. Such a mysterious thing, and we will learn a lot about it.
What advice would you give to today's physics students? Would you encourage them to follow you in this field? And what advice do you have?
Especially experimental physics. Here, up there in there.
And I happen to believe that aliens speak physics too, so you can communicate with the aliens in physics.
Well, my last question is, if we in the audience want to stay up to date and follow along, or find a way to get involved in some of this future effort, what would you advise us?
Come to events like this one. There are actually tons of great public lectures being given in all areas of science, but also in particle physics and cosmology in particular. And you can also, look up on the internet. Exactly. And some of them are wrong. You have to be careful about that.
Fake news.
But some of the fake news. But there are actually a lot of great material out there. So yes. I really encourage people to check them out.
Mm-hmm.
Or come and visit CERN.
At this point, we would like to invite Danielle back to the stage with us, and we will open this up for your questions, if you have any.
Thank you. So I actually just wanted to add something to the last thing about the question about how you can get informed or stay informed. So I'm also a physicist at Atlas, and I recommend going to the CERN website, to the Instagram accounts of all the 4 big experiments. And you can also do a virtual visit of the Atlas experiment, for example. So you don't actually have to go to CERN, you can start virtually.
Yes. But ultimately it's nice to come to CERN. Ultimately, I'm saying. You can start with a virtual visit, but seeing the real things. So, yes.
I have a question in the meantime. I'd love to run through some of your career highlights for each of you here. Really exciting moments in your career. When you look back, what will you especially remember?
The discovery of the Higgs boson. Yes, 4th July 2012, when the Higgs boson was, when we announced the discovery of the Higgs boson. That was the day.
And it was still on the web.
Yeah.
It was very exciting too.
I think it was seen by 1 billion people.
Yeah.
It was absolutely fantastic day. So, and the result of decades of work of the worldwide community, thousands of people, and being able at the end to see that very special particle, and so special because, as you've seen, it doesn't fit with the other families of particles. It has a special role. It played a special role in the early universe. It carries a different type of interactions, as very special features. So that was something really memorable.
I don't know if this is actually positive excitement, but when I was in grad school, and I, of course, have to write a PhD thesis to graduate, and the work I have done for the PhD is to write a piece of software that would allow people to simulate what happens when you smash particles against particles. And it's still being used today. But as a result of this thesis I wrote, I nearly failed the defense, and I was almost, lost it out of the field, because the experimentalists on the committee said, well, he calls this data, but it's not experimental data. And theorists on the committee said, well, he calls it theory, but just a piece of software. Is this physics? And so that was a big adrenaline falling from my head at the moment. So it's a negative excitement. But the message here is that, things can happen, but if you actually persist at some point, you will be fine. So that's my message.
And I believe you got your PhD in this.
We don't discover particles very often. The top quark, the Higgs boson, these are decades apart. And so for me, one of the most exciting moments was a time we didn't discover a particle, but we thought we might. I remember a student came to me with some piece of data, and we looked at it together, and we thought, oh my gosh, this looks like a discovery. There's this beautiful peak. For the physicists in the audience, it was 105 GeV between 2 same-sign muons, and we couldn't explain it. We looked at this and we thought, oh my gosh, is this the moment? And that's the excitement of experimental physics, is that you never know what's in the data. The universe has surprises. They're waiting for us. You never know, is it around the corner? Is today the day I see the plot that changes the history of human intellectual understanding? Turns out it was just a fluctuation, and we looked at more data and it went away, and it was nothing. But we had so much fun for like a month trying to figure out, what was this thing? Could it be wrong this way? Could it be wrong that way? Could it be wrong the other way? It was a lot of fun, even though we didn't actually discover anything.
Any other questions? Yes.
Yeah, for string theory, I don't know how popular that still is among theorists, but are there ever going to be any machines that can test string theory and see if what it predicts is true?
I guess I have to take it, this one.
Yes.
So,
You can't escape.
So string theory, for those of you who haven't heard of it yet, is supposedly theory of everything. And Daniel talked about 4 forces in nature: weak force, strong force, electromagnetic force. And these 3 forces mesh very well with each other. And there's something called quantum field theory that describes these forces extremely well. But gravity, which is the most familiar force to everybody, is actually least understood. And it doesn't seem to mesh well with the other forces. And the string theory was supposed to actually put them together under a single framework so that you can understand all forces on a single shot. But so far, they haven't come up with some testable predictions that can be tested by experimentalists like Fabiola. And so we don't know if this is true. And also, string theories actually happen to predict too many kinds of universes. And so this universe is only one example which may come out of string theory, but there's tons of others, and that's the idea of multiverse. And so that is also a very difficult test because nobody has gone to a different universe and come back here. So right now, we don't know if the theory has any relevance to the real world, but the people are still trying to make sure, to figure out what exactly the predictions are of string theory, and hopefully, eventually, we may be able to test if the theory is right. So that's where things are. Does that answer your question?
Hitoshi, did you specialize in supersymmetry? Do I have that right?
Yeah, so the supersymmetry is an idea that is sort of something that came out of string theory. So even when string theory itself may not be the right idea at the end of the day, it actually spawned many other ideas which can be actually relevant for experiments. And the string theory is actually called superstring theory because it has something called supersymmetry in it. And because it's called super, it's a great symmetry beyond anything we have seen so far. And that actually predicts new particles that may be actually detected at the Large Hadron Collider, and people working very hard looking for them. Some of them actually end up being dark matter in the universe. So it has actually some testable predictions that way. Yeah. So that's something the people working hard to actually figure out if that really makes sense in view of the experimental data.
Nothing until now.
We found nothing until now.
But you know, we can never tell what the benefit is going to be of some theoretical idea or mathematics. There are people out there who think about new mathematical ideas and spend decades playing with them just because they think that's fun. And then 50 years later, some physicist is like, oh, this is really useful. It actually describes something fundamental about the universe. And so we should definitely be exploring things, even when we don't know how they're going to be relevant. They will eventually tell us something about the universe.
Mm-hmm. I have a question on how the research at CERN is related to, say, mass manipulation of fusion reactors at ITER, and is there any cross-collaboration for those kind of activities?
Yes, I am going to reply. Yes, there is. And the relation and the collaboration are on the technologies. So, for instance, fusion uses superconducting magnets, to confine the plasma. And CERN has a lot of expertise on superconducting magnets, in particular because the requirements in terms of magnetic field uniformities in accelerator and colliders like the one that we operate or we will build at CERN are much more stringent than the quality of fields for fusion. So, in some sense, the magnets that we have to develop for particle physics are much more demanding than for fusion. And so we actually have been collaborating with ITER, helping them build their coils. And so there are many, many collaborations like that through the technologies.
I think you were hoping we were going to shoot a beam into the fusion device or something, right? Yeah.
Yes.
With the wave-particle duality, what are your personal relationships with the word particle?
We are made of them. That's a personal relationship. And the particle-wave duality is a very strange idea, right? What is supposed to be a particle, like an electron, actually behaves like a wave. What is supposed to be a wave, like electromagnetic wave or light, behaves like a particle. But you actually need it. Otherwise, atoms wouldn't be stable in your body because the atoms are made of nuclei, electrons go around it. If you think of electrons just like a particle, why doesn't it spiral into the nucleus? Because they attract each other by the electric force. But it doesn't because it is actually a wave at the same time. And once you actually make an electron a wave, it can spread out and doesn't shrink all the way to a point. And that's how our atoms are stable. So our existence actually relies on this particle-wave duality, that the way electrons behave. So that's very personal.
If you ask 12 different theorists what is a particle, you might get 12 different answers.
12.
And 30 different answers. And one of the reasons is that we're limited here because we're describing things that are fundamentally counterintuitive to us. We have no analog for. It's like you're trying to explain the rules of basketball only using baseball analogies. It's going to be clumsy, and it's not going to work all the time. So we say, oh, it's a particle, oh, it's a wave. Really, it's neither. It's something else weird and different that we can never completely capture with any of our intuitive language. And so we try to describe it a little bit. You know, it's like you drink a new glass of wine and you're like, oh, it's a little bit of oak and cherry and whatever. And like, it doesn't have those things in it, but that's your language for describing it. And physics is about describing the unfamiliar in terms of the familiar. But it's always going to be limited.
We had some questions in the back.
Perfect. So with all the different accelerators getting stronger and stronger at CERN, what are you guys aiming for with the FCC? Like, how much stronger will it be than the LHC?
So the FCC actually is not a unique, is a facility. It will be a new tunnel which will host in a first stage an electron-positron collider, so colliding electrons and anti-electrons. This is what we call a Higgs factory, to study the Higgs boson with high precision. So here the point is not so much the energy, the point is being able to produce many, many Higgs boson in a very clean environment and to study them with very, very high precision, to answer those questions related to the Higgs boson that were mentioned before. Then there will be a second phase, which will be a hadron collider like the LHC. And so with the hadron collider, with the future circular collider in hadron collider mode, in proton collider mode, we can make a jump about a factor of 7 to 10 in energy. And so this will allow us to, to study the next energy frontier and maybe try to answer questions related again to dark matter or to many, many other questions that at the moment, we don't understand. Like, Danielle showed, for instance, the the families of elementary particles with masses that span many orders of magnitude, from neutrinos, which are super light, to the top quark, which is extremely heavy. We don't understand why it's so complex. We don't understand, nature is usually very simple and it's very rational. And very often in physics, when we see complexity, or if you want, things that seems to be quite random, and there must be some underlying symmetry or underlying principle that can explain this kind of diversity. And so this is another type of question that we will try to address with the future circular collider.
Hey, Professor Murayama, I actually have a question. So as a student who's trying to maybe become a theorist someday, there's just so much, every time you learn something, there's so much more that opens up. How do you know, or how do you get to the point where you can start contributing to a field, right? I guess, do you have any advice for that?
So if I remember how I was feeling when I was at grad school, I felt like, I don't know enough to be able to do anything. And it turns out I still feel the same way today. And because, you never know, you would never come to the point that you know everything you need to do research and contribute to the community. You never get to that point.
Yes.
And you have to sort of struggle on its way. But then you soon realize that even though you don't know enough, you still can do something. And then start actually writing papers and collaborating with the people around the world and making friends everywhere. So, you actually, it's really surprising. But, you don't need to feel like you have to study very hard so that you have learned everything you need to be able to do research, because you never get to that stage. You can produce something even when you don't get there, because there's always something that you know a little bit better than other people. You may have a little better idea than the other people, and that is actually enough to actually contribute to the scientific community. So, you just gotta try, and that's my message. Professor, course, given the track record of misleading people like Fabiola, trying to look for wrong things, right? So you can always make wrong predictions.
I believe we also have a question in the back middle.
Professor Murayama, could null results in collider searches for beyond standard model physics, supersymmetry, and dark matter lead theoretical physicists to postulate new avenues or paradigms for confronting the big questions, in a similar vein as the null results in the Michelson-Morley interferometer experiment ultimately led Einstein to think about space-time in a new way and come up with special relativity?
So that's a great question, so the theorists often come up with ideas and suggest experimentalists to look for them, and often they don't find them. and then we get proven wrong. But not finding something is actually a great way of learning something important about the way the universe works. Because if you don't want to spend the infinite amount of time looking for something that is actually not right, but you want to quickly learn if something is not right, it is not right. And then you can stop and go in the other direction.
Exactly.
So learning something that is not true is actually a very important piece of information for all of us. So that's how I justify myself.
Yes, no, but it's, I agree, and we're discussing this before. I think that the importance of research is, of course, discover new things if we find new things, but also to redirect our thoughts toward more promising direction, and as I was saying before, to understand what are the real questions to ask, because we're not sure that we are asking all the important questions that for sure we are missing something big, by the way, because all these open questions, dark matter, dark energy, and many others, really show that we are missing something big.
When you name stuff like wimps and machos, is it like one person making all those jokes, or do you guys agree on them?
You brought them up. So.
Particle physics is terrible about naming things. Usually we think, oh, this is similar to this other thing that's completely different. So we're just going to borrow that name even if it's very confusing. So we talk about quarks having colors and flavors, even though they don't literally have any color or flavor. But this is, again, because we're borrowing analogies, because we don't really have any intuition for what's going on here. So those were actually not jokes. Those were serious names that people gave them in an effort to be, serious scientists. But yes, we definitely do need to get our naming under control. I agree.
Yeah.
At a certain point in your careers, I guess you've transitioned from an individual contributor to like a position of leadership. And I'm just curious, with academia, how did you find that transition? Do you find yourself going from think of your own theories and thinking of your own experiments to managing other people's experiments and theories? How has that transition been for all of you?
I don't know. So as I was responding to some of the prior questions, you don't make transition all of a sudden. You gradually make the progress. And I remember the first time I could ever write a paper back in grad school, and that was certainly an exciting moment. But of course, the paper I wrote back then, nobody was interested in reading it because it was not a really great result. But it was a good actually way of building my confidence that I can at least do something. And only after many, many years, I start doing something that catches people's attention, and people start reading my papers. And it's very gradual. So there's no sudden transition that all of a sudden you become, rich and famous. Yeah, that's the way it is, I think.
Yes, the same for me. It came gradually. It's not that when I was, 17 years old, I said, I want to study particle physics to become Director General of CERN. No, that was not at all my... but it comes gradually, and at some point, it's also correct that people with some seniority at some point do take responsibilities and do also part of the administrative work to let the young people do the most funny part of it, which is the research. So I think in our field it comes quite naturally, and we remain physicists. I mean, my job today is not really to do research with my hands, is more, but I still continue to do science, more in terms of strategies, more in terms of, thinking about the future, where we are going, what we are going to do in the coming years, like Hitoshi has been doing also with this P5 panel. We continue to be physicists, and it's just that for some years we play a different role. So when I will finish my job as Director General, I will go back to do research. And so it's a kind of cycle, and voila. You said it. So.
I think there's lots of different paths in particle physics. It's not a straight line between zero and becoming, the Mick Jagger of theoretical physics. there's lots of different paths you can take. And one of the things I love about particle physics is that there are so many directions. Everybody gets to do the bit that they're most excited about. So maybe you really like organizing people and becoming management, or maybe you just want to work in a lab and run the computer systems. There's room for lots of different kinds of people who are excited about lots of different challenges. So there's lots of different directions, not just one path through the field.
Just speaking as a science journalist, there's also many journalists who make their full-time living writing about physics too. So that's an option too.
Yes.
So the early 20th century seemed to be one of the most exciting breeding grounds for theoretical physics. It really seemed to be a very exciting time. I myself am more an experimentalist, but I do think about theoretical physics. I do ponder the wave function almost every day. And I noticed that there is a decline in the creativity or what has been produced in the field of theory. And I want to ask, what are your comments on why this is, and if, doctrine or has anything to do with it, things of that nature?
Well, the theoretical physics is actually always exciting, because what we do is really trying to figure things out. And one of the, I'm a particle physicist, but actually I was teaching in Berkeley, and there was a student who actually is more interested in the property of material. And he asked a bunch of questions during the class, and one of the questions he asked actually made me think, that's an interesting question. I don't know the answer to that. And then we actually start to work on this together. And the question was very simple. It turns out that there's a theorem in theoretical physics that predicts certain things, but that theorem doesn't work on a piece of magnet on your fridge. Something is wrong. And it turns out that there was a simple answer, because if the theorem is wrong, the assumption was wrong. And so we actually wrote the paper together by saying that, okay, we now understand the Higgs boson and a piece of magnet at the same time. So that's the kind of thing what we love to do. The theoretical physics is really about explaining many different things that looks totally different from each other, but there's some underlying principle for all of them. And that would, I'm sure, continue on forever, actually. So this is an exciting time for all kinds of reasons, but I'm sure it has been exciting in the past as well, and it will be exciting in the future too, because there's so many things we haven't figured out yet, and I'm sure somebody can figure these things out.
And remember that physics is just people. There's no doctrine, there's no central committee telling us what to study and what's okay. It's just a bunch of people curious about the universe trying to figure it out. And I hear a lot of discussion of, physics is dominated by doctrine, or there's been a stifling of creativity. And I'll tell you from the inside, I don't see that. I see a very vibrant community filled with people having creative ideas and talking about them. Some of those ideas aren't the things somebody else might work on, or they think something else is most exciting, but it's just a bunch of people following their ideas, and maybe it'll change direction and go this way or that way, but people are curious, and you can't tell them what to do.
Yes, please.
Hi, I have a question for all four of you. Talking about creative ideas, do you look for inspiration or ideas outside physics, like from or have you been inspired from fields like arts, literature, music? How does has it influenced, or do you look for inspiration from those fields?
Yes.
I believe we actually have some musicians on stage.
No, don't exaggerate. Unless you're talking about the two of them.
I think all three of you have backgrounds with instruments,
Yeah.
Is that right?
Well, actually, I have a background in humanities and in music, and then I decided to study physics. And very often people ask me, but how it comes that you moved away from humanities and music to physics? I didn't move away from anything. I continued to work in the same thing, because, culture is just the same thing. Music, like physics, are the expression of human curiosity, creativity, wish of exploring, there are so many links between the two. For instance, we talk about complexity in nature building upon simplicity. The fundamental laws of nature and elementary particles, they are very simple. You have seen in the movie, you can write the equation of the standard model in 3 lines, similar for Einstein field equation of general relativity. So it's very simple, complexity built on simplicity, up quarks and down quarks and electrons. Music is the same thing, very complex symphonies built out of 7 notes. So there are so many strong links between arts and science for me, for music and physics. And I used to say that what I'm today as a physicist, I owe it to my physics studies as much as to my humanities and music studies.
And actually, part of the reason why I got interested in physics was music. And when I was in high school, when I was in middle school, I actually happened to live in Germany for a while. And that's when I got attracted to prog, progressive rock, like Pink Floyd and Genesis. Some of you know these bands. And then I started playing bands. And then I just got curious, if you play different instruments with the same pitch, like the sound of A, why do they sound so different from each other? And when I was in high school, I actually got into the physics lab, and I started actually watching the sound wave on oscilloscope, and they look different. And then all of a sudden you understand why clarinet sounds kind of hollow, why violin has such a rich sound. And so once you actually get to see these things, and that can be all understood by physics.
Yes.
And so that was really amazing to me. So music has actually a lot to do with physics, and that was the reason, part of the path I actually came through, how I got attracted to physics to begin with.
Daniel?
I haven't found inspiration in art or literature, but I think there's a lot of inspiration to be found in adjacent fields. For example, I talk a lot to computer scientists and statisticians, and a lot of times the questions we're asking are questions they've never heard before. It inspires them to build new tools to solve our problem that nobody's ever tried to solve before. Or we discover, wow, they've been building a tool that we can use to solve our problem, and so we can borrow it. And there's been a lot of incredibly fruitful overlap there. Machine learning, for example, is a huge industry. Facebook spends more on, is this a picture of your cat than we do on discovering new particles. It's incredible, the scale of the funds we're talking about here. The amount of money people spend on new cell phones every year dwarfs CERN's budget by orders of magnitude. So whenever we can take inspiration from those fields and the creative ideas that come out of that kind of research, we definitely take advantage of that.
I have a question about AI. What is your take in particle physics to move forward? Could this be used to, dig into these huge amounts of data? Could this be put together the pieces that human brains in limited capacity to look at data cannot do? What are the plans, for example, for CERN to look at this, and do you think this could open a new era of discovery?
It's for sure, and it's any new technology, of course, it must be considered and it can be helpful. So AI is not new to CERN, and we have been using artificial intelligence or similar technology already in the past, and we continue to use them. And you said it. We have to extract. Sometimes we have this huge amount of data, and we have to extract these very tiny signals. For instance, the Higgs boson itself is not produced so often, and in the case in ways that many cases are swamped by huge backgrounds. So you have to extract this very tiny signal out of a huge background, and so this you can do much more effectively with machine learning or automated techniques. But we also use artificial intelligence in some part of the operation of the accelerators, for instance. And also, if you think about the future circular collider, which will have a 3 times longer circumference than the Large Hadron Collider, you can't think of running such a big facility by hand. You need robotics, you need automation, you need artificial intelligence. So for sure we will be using those technologies even more.
All right, I think we have time for 1 or 2 more questions. We have one back here.
Hi, I think you hinted at this a bit already, but I was just wondering if you could talk a little bit about how much of your jobs is devoted to trying to get funding for your research and how big of a challenge that is.
A tiny bit. So I must say I'm lucky enough in my current job that most of my time is still, means more than 50%, is still devoted to scientific/technical problems, so issues, technical issues, or science in terms of planning, strategy. Of course, I also have to devote a non-negligible time to funding, to budget, to see, also the budget and funding part is sort of interesting and amusing. Because, in general, physicists, we do like problems. If there are no problems to solve, we get bored. And so when you have a limited funding, like the CERN budget, and then you have to get most of it, the largest possible amount of project and results from that budget, that of course is an interesting problem to solve. So that's quite challenging to see how to use the budget we have in the best possible way and funding as many and doing as much physics as we can. But also what is clearly challenging and interesting is to find the money for future facilities. So it's also an interesting challenge and an interesting work in terms of relations, ideas. It's an important fraction, but as I said, the dominant fraction is still the scientific part, and so that's why I like my job.
I spend a good fraction of my time writing grant proposals and trying to get funding. And you should understand that, as Hitoshi said, physicists are very creative. Like in every field of science, there's way many more ideas that people have that are very deserving that are funded. And I'm not a politician. I don't understand why we don't invest more money in basic research. If all these really clever people coming up with really great ideas that could tell us about the universe, we could basically just buy knowledge about the universe, and we just don't as much as we should. So I don't understand why we don't multiply scientific funding by a factor of 10. I think it would be a great investment in our society and in ourselves and in our future. But that's how I feel about it.
Any closing questions for us?
Okay, getting really fundamental for the last one. Why are there only 4 forces? Where's the 5th force? Where's the 6th force? Could they explain a lot of the questions that we're talking about here?
There could well be. And, again, as a theorist, I once predicted many more forces than 4 and had not been discovered yet, but there could well be. And in fact, in some sense, we actually already know that there are more than 4 forces because, as Daniel said, Higgs boson, which is frozen in the universe everywhere, seems to interact with different strength to different particles. That's why they acquire different masses. And so each of them has different size of the force for some reason, and we don't understand why, but there are actually a huge number of forces if you actually look at it that way. So there's definitely more than 4. How many forces there are, again, that's something we don't know yet.
But we already have so many problems with 4 forces that...
Fantastic. Well, we'll leave it there. Please join me in thanking our panelists for this very enlightening, inspiring evening.